You're a high school chemistry teacher and you are wondering which problem or project-based learning module should you implement into your chemistry curriculum. The project that I'm going to advocate for in this video is titled, Why Does It Matter What's in the Water? The project focuses on the salt in the water. No, not necessarily the salt that we add to our foods to make it taste better. Instead, this project focuses on the salt that we tend to throw on our roads, especially in the northeast of the USA as well as Canada. In particular by the salt trucks during the winter months, but it could even extend into the early spring. If we look at the following graph released by the United States Geological Survey, you can clearly see that the use of road salt has been increasing based on this data from 1975 up until 2017. We're talking between 20 to 30 million metric tons of sodium chloride used for de-icing the roads in North America. But the use of road salt is really a global problem. As you can see by this study, which was a collaboration between MIT, UMass in the USA, as well as the Hebrew University in Jerusalem, Israel. This is based on data from up to 10 years ago, and we're looking here at 3 different pathways that result in an increased use of road salt. The first pathway, pathway A, states that sodium chloride is now an effective de-icer due to the warming of Earth. The second pathway that would call for a greater need of road salt is due to the increase in freeze-thaw events, again as a result of climate change. The third pathway that calls for an increased use of road salt is because of more snow and ice due to an increase in winter storms. The graph mainly focuses on locations on the northern hemisphere, in particular the northern part of the USA as well as Canada, and several locations in Eastern Europe extending well into Russia. This PBL module centers around the following phenomenon: road salt usage and its associated environmental and health consequences. The question that this PBL module is really asking is, how much road salt are these trucks releasing? And to what extent is that road salt having an effect on wildlife, including the ecosystems in particular in central and upstate New York? Based on a report conducted by the Carey Institute of Ecosystem Studies, 90% of the salt in a watershed can come from road salt. And that road salt runs into nearby streams and groundwater. Let's emphasize the standards that are associated with this PBL module. First, I'm going to focus on the NYSSLS standard, namely the New York State Science Learning Standard, HSPS 1-10 solutions. Use evidence support claims regarding the formation, properties, and behaviors of solutions at bulk scales. It also emphasizes the following NYSSLS and NGSS standards, namely ETS 1-1, 1-2, and 1-3. And ETS stands for Engineering, Technology, and the Application of Science. And that's what makes this PBL module so important. Which are these 3 ETS standards? ETS 1 reads as follows: analyze a major global challenge to specify qualitative and quantitative criteria and constraints for solutions that account for societal needs and wants. The data which I just showed you certainly underscores the importance of this matter. ETS 1-2, design a solution to a complex real-world problem by breaking it down into smaller, more manageable problems that can be solved through engineering. This PBL module will definitely address that. ETS 1-3, evaluate a solution to a complex real-world problem based on prioritized criteria and trade-offs that account for a range of constraints including cost, safety, reliability, and aesthetics, as well as possible social, cultural, and environmental impacts. We will address that with this PBL module as well. This PBL module opens with the following central question, as you can see in this student handout. How do the contaminants get into the water? I start off this PBL module by showing my students the following video, which really shows how these salt trucks release a lot of salt on the roads and how the Lake George watershed in New York State has been experimenting with alternatives to the use of regular road salt, which is mostly composed of magnesium and sodium chloride. Further reading also includes the fact that Road Salt Reduction Act was signed into law only a couple of years ago, back in December 31st of 2020. Based on the video as well as the background reading, students write down notes from what they've learned so far. Next, the handout delves into some more detailed background information as it relates to limnology, the study of biological, chemical, and physical features of all inland water. It introduces some vocabulary terms, including watershed and runoff, and then delves into road salt usage in both the Adirondacks and central and upstate New York. And students are then asked to basically come up with at least 5 questions based on that background information as it pertains to the usage of road salt. After this introductory anchor, which has hopefully engaged your students, the handout then continues into 7 tasks. Task 1 emphasizes the graphical analysis of the sodium chloride concentration in northern New York. The second task involves an investigation and is thus very hands-on, namely, why do we salt the roads? The third task focuses on the environmental impacts of the use of road salt. We're focusing here on 2 different graphs. The left graph is a bar graph that clearly shows that in the presence of roads, there's a lot more of both sodium and chloride ions compared to in the absence of roads. And this is based on the median concentration in milligrams per liter. The graph on the right shows you a scatter plot. And based on the linear regression with an R-squared value of, let me read here, 0.84, there is a relationship between increased road density and the concentration of both sodium and chloride, again in milligrams per liter. The third and last graph that the students are answering for this first task focuses on sodium and chloride ions in Mirror Lake in Lake Placid. The left y-axis emphasizes the depth, so you have to follow the black line across the graph. If we look at the 2 arrowheads, the first peak is in the winter of 2017, when total chloride has reached levels as high as 180 to 185 metric tons. And the greatest amount of chloride ions is at a depth of about 16 meters. The second peak is in the winter of January 2018, when total chloride numbers reached upwards of 175 metric tons. And the greatest chloride amounts were located at about 16 plus meters depth between roughly 110 to 130 milligrams per liter. After completing the analysis of these 3 graphs, the students are ready for the second task. The second task asks students to investigate, why do we salt roads? And they get the following prompt. Plan and carry out an investigation on how the addition of salt affects the freezing point of water. This shows you the heating curve of pure water, and the arrow points at the second part of this graph, where solid ice is melting. Here, I give my students a supplemental lab. The lab is titled the Freezing Point Lab. See the link above that details a video that explains this lab. It helps students be prepared to actually tackle this second task of this PBL module. So in order to plan and carry out this investigation, they are instructed to complete the following Wonder of Science diagram. I'm showing you here an example of what some of my students chose to investigate. The research question reads as follows: how does the addition of salt affect the freezing point of water? The independent variable is the amount and type of salt added, compared to the dependent variable, which is the temperature of the beaker content. It details the lab setup as well as the constants that they intended to keep controlled as they carried out this experiment. And the data was collected in Google Sheets. By adding equivalent amounts in moles of either sodium chloride and magnesium chloride to a set amount of ice water, my students noticed the following. First of all, which was a little oops, the starting temperature of the ice water prior to adding the two different salts was not the same. The beaker to which magnesium chloride was added started at a higher temp compared to the beaker with ice water to which sodium chloride was to be added. One of my students decided to mess with the thermometer and actually blow some hot air onto the thermometer probe, thereby increasing its temperature artificially. The final temp for the two different beakers was pretty close, and therefore I encouraged my students to really focus on the difference, the delta in temperature drop, as shown in the following bar diagram. Clearly, when adding an equal amount of moles of magnesium chloride compared to sodium chloride, there's a greater temperature drop of the slushy ice mixture. What you are not seeing in this graph is a control to which no salt was added in the first place. To conclude this second task, students are instructed to write a claim evidence reasoning statement. Again, the question that they were to answer was, how does the addition of salt affect the freezing point of water? To answer that question fully, I really had to do some direct instruction so as to coax them into writing the best reasoning component of that CER statement. Why do we salt the roads? Well, there's something that salt does to the freezing temp of water. When water likes to freeze through the formation of hydrogen bonds, it can only do that by excluding any of the other particles, such as sodium and chloride, in solution. So if any other solid particles are added to this icy slush, it would impede with that freezing process. The third task enables students to read up on the environmental impacts of road salt usage. I'm going to highlight 3 of the studies that are emphasized in the handout. The first study focuses on road salt contamination and its possible effects on the sex ratios of wood frogs. The left image already shows you the disastrous effects of salt usage on the quality of the eggs from these frogs. The second study highlighted in the handout is road salt's negative effect on rainbow trout. Based on the data shown here, increasing the amount of such salts, including sodium as well as calcium chloride, it certainly has an effect on the size of the rainbow trout. The third study highlighted in this module is a review of the combined threats of road salts and heavy metals to freshwater systems. When road salt is absent, there's only a certain amount of heavy metals released into the groundwater. However, when increased amounts of salts are running off and entering the groundwater, it manages to extract any heavy metals present and take these heavy metals with it into the groundwater. That concludes the first 3 tasks, which is a very manageable amount to complete in your high school chemistry curriculum. The amount of time it took me to complete these 3 tasks would be roughly 4, maybe 5 class periods. And my periods at my school are about 50 minutes in length. I'm now going to much more quickly go through the remaining 4 tasks. I did not get to these remaining 4 tasks this school year, maybe next year. In the handout, I've highlighted these last 4 tasks as an optional extension. Task 4 gives the students an opportunity to explore the water quality data as released by the New York State Department of Environmental Conservation. This definitely requires that you have a strong Wi-Fi connection because they are going to the DEC site and basically loading the various data sets available at all these different points across the state of New York. Here I'm showing you the vast amounts of data that we collected. The colors refer to the different types of topography found at that area. These 4 include in red, urban, in orange, residential, in yellow, agricultural, and in green, forest areas. When plotting these chloride amounts found on the DEC site in a Google Sheets histogram, you could see the following data. The overall big idea takeaway is that in areas where there's mostly forest, you see a lower concentration of chloride ions present in the watershed. Whereas in urban and urban/residential areas, you see that the chloride amounts are definitely higher, peaking at roughly 400 to 500 milligrams per liter water. As we look at these chloride concentrations across New York State, and then thinking about the effects that these chloride ions can have on the environment, one wonders if there are any alternatives that we can use instead of regular sodium chloride and magnesium and calcium chloride in our rock salt. So at the end of this PBL module, students get a chance to investigate alternatives. These particular alternatives are presented by the report of the Carrot Institute that I referred to earlier. Let's take a closer look at some of the alternatives. Shown here are road salt or rock salt, which have a low direct cost and a moderate aquatic toxicity. The bottom part of this diagram looks at some other road salt alternatives. The unfortunate part is that their relative direct cost is high, other than sand, but sand may not work as well, although is good for friction. An advantage is that these alternatives, although high in terms of cost, are not very corrosive. Their aquatic toxicity is only indirect, and besides these three road salt alternatives, including calcium magnesium acetate, potassium acetate, as well as sand, and often sand is mixed in with the regular road salt, some other options you may have heard about, including beet juice and possibly pickle juice. Whether beet or pickle juice can actually beat the effects of road salt on the freezing temp of water, that's a good question to ask, as they come up with their final question, claim, evidence, reasoning statement that really incorporates these alternatives and their possible effectiveness on the roads. So in summary, this is a PBL module that can be considered to incorporate in the chemistry curriculum at the high school level. There are 7 tasks total. The first 3 are absolutely key to start with: background information, an actual hands-on experiment that allows students to see what the effect is of salt on the freezing temperature of an ice slushy, and third, to actually read about the impacts of road salt on the environment. The remaining 4 tasks looks at data across New York State. And finally, what are some possible cost-effective, but also from a freezing point perspective and road safety perspective, good alternatives to road salt? And then finally, that final QCER statement brings a closure to the entire module. What is the key question that this PBL addresses? What is the claim, the evidence, and an explanation, the reasoning as to completing this? If you're interested in obtaining these resources as well as the associated keys, check the link in the description below. In exchange for your email, you get a link to the following Google Doc with not just the PBL lesson handouts, but any other chemistry associated handouts, as well as teacher keys and the connected videos. Thank you very much for watching. Bedankt voor het kijken. Tot ziens and see you in the next video.